Hello everyone, myself Dr. Santame Kundu. I welcome you all to this lecture of soft computing techniques. This is the first lecture of module 12. In this class, we will study the introduction part of artificial neural networks. Artificial neural networks were developed in the year 1980 as a way to model complex patterns and make prediction based on data, drawing inspiration from the human brain structures and function. These networks are designed to simulate the way neurons in the brain communicate and process information, enabling machines to learn from experience and improve performance over time. The breakthrough in ANN research came in the year 1985 when Geo Finton and his colleagues developed the backpropagation algorithm, which allowed networks to be trained more effectively and efficiently. This algorithm enables ANNs to adjust the weights of connections between neurons in response to errors, significantly enhancing the learning process. The formation and architecture of artificial neural networks have evolved over the years with advancement in both theory and computational power. The initial focus was on shallow networks with a few hidden layers, but the increasing ability of large data sets and more powerful computing resources has led to the rise of deep learning techniques, particularly deep feed-forward networks. These deep networks, which consist of many layers of interconnected neurons, have become central to modern artificial intelligence research and applications. Today, neural networks are a rapidly advancing field of study, attracting considerable attention from both academia and industry. They have made remarkable strides in various domains, including natural language processing, where they are used for tasks like language translations, sentiment analysis, and chatbots, image processing, where they power facial recognition, object detection, and image generations, and autonomous systems such as the training of self-driving cars, where neural networks helps in decision making and navigations. Furthermore, ANNs are being utilized in healthcare for diagnostics, in finance for algorithm trading, and in robotics for improving automation. The continued evolution of neural network is poised to further revolutionize many industries, leading to more intelligent, adaptable, and efficient systems, with deep learning methods pushing the boundaries of what possible. The potential application for ANN-based technologies seem limitless, making them a cornerstone of modern artificial intelligence. Artificial neural networks are a class of machine learning models that draw inspiration from the structure and functioning of the human brain. These models consist of layers of interconnected neurons, that is processing units, that transmit and process information. Each neuron receives inputs and processes it and passes the output to the next layer, enabling the network to learn from the data and make predictions or decisions. So here is the two figure. One is the human neuron, another is the artificial neuron. So here dendrites, that is the part. Here also these things that receive signals from other neurons and transmit to the cell body, that is soma. So here also the same concept. Here also receive the input. Here it is processing with the activation function and find and calculate the output. So that is output action, just like the same structures. NNs come in various architecture, each with its own specific features, application, and strengths. Some of the most common architectures include feed-forward neural networks, that is FNNS, the simplest form of NN, where information flows only in one direction from the input layer to the output layer. There are no cycle or loops in the network, and the layers are fully connected, just like this. The next one is that recurrent neural networks. These networks introduce a memory component where information can loop back on itself, enabling the network to process sequences of data such as time series or speech. This architecture allows the network to maintain context over time, making it ideal for tasks like language modeling or speech recognition. The most important one is that convolutional neural networks, that is CNNs. Primarily used for image and visual data processing, CNNs use convolution layers to detect specific features such as edges, textures, and shapes in an image. Pooling layers flow the convolution to reduce the spatial dimensions of the data, making CNNs highly effective for tasks like image classification and object detection. Neural network with a convolution operation instead of matrix multiplication in at least one of the layers. Traditional neural networks, in most neural networks, matrix multiplication is the core operation in each layer. The input is multiplied by a weight matrix followed by the application of an activation function to compute the output. Convolution layer, a convolution operation replaces the matrix multiplication in certain layers. Convolution neural networks use this operation primarily for tasks involving spatial data like images and videos. Convolution involves using filters, that is kernels, that slide across the input to extract local features. Advantage of convolution over matrix multiplications: fewer parameters. Convolution reduces the number of parameters compared to matrix multiplications as a single filter is applied across different regions. Local operations: filters only operate on a small patches of the input, which is more efficient, especially with large or high dimensional data. Reduce computation: convolution operations are computationally less expensive than matrix multiplications, resulting in faster training and inference. Improved feature detection: convolution helps the network detect local patterns such as edges, texture, or shapes, which is crucial in tasks like image recognition. It preserves spatial hierarchies, meaning the network learns the structure and relationship between features in the data. Better generalization: weight sharing in convolution layers seems the same filters are used across the different parts of the input, helping the network generalize better. This reduces overfitting and allows the model to recognize features at various spatial locations in the input. Translation invariance: convolution layers provide translation invariance, meaning the network can recognize the same feature regardless of its position in the input. Common applications: CNN with convolution layers are ideal for tasks like image and video classification, object detection, and segmentations. They are also increasingly used in natural language processing tasks such as text classification, where the spatial relationship between words or characters are significant. Comparison to fully connected networks: the fully connected networks rely heavily on matrix multiplication, which can lead to a large number of parameters and require more computational resources. Convolution layers offer more efficiency, especially when dealing with high dimensional and structured data. Network architecture: neural networks with convolution layer can be hybrid models where certain layers use convolution while others still use matrix multiplications. As for example, the fully connected layers at the end of a CNN. Next one is that autoencoder. These are unsupervised learning models that aim to learn a complex, a lower dimensional representation of the input data. An autoencoder consists of an encoder which complex the data and a decoder which reconstructs the original data. Autoencoders are often used for tasks like anomaly detection, data compression, or image denoising. Next one is that generative adversarial networks, GANs. GANs consist of two models: a generator that generates new data samples and a discriminator that distinguishes between real and generated data. GANNs are used in generative modeling such as creating realistic images or generating synthetic data. The model of artificial neural networks can be specified by three main components. One is interconnections, second one is activation function, and third one is learning rules. First one is that interconnections. So interconnection defines the structure of the network, describing how the neurons are connected to one another. These connections are typically associated with weights and adjust during the learning process. The structure of these interconnections plays a crucial role in determining the capabilities and performance of the network. ANN is generally have three main layers. One is input layer. This layer buffers the input signals and provides them to the network. Hidden layers. These intermediate layers process the input data. They are hidden from the user and are not directly observable. Increasing the number of hidden layers can improve the network's ability to handle complex tasks but also makes the training process more computationally expensive and complex. Output layers, the final layer produces the network's output based on the process done in the hidden layers. Additionally, there are five common types of neuron connection architecture. One is the single layer feed forward networks. In this architecture, there are only two layers, the input layer and the output layer. No computation occurs in the input layer, and the output layer is generated by applying different weights to the input. The network computes the output based on the cumulative effect of the weighted input. So these are the input, is y output. So here you can write y1 input k is summation of I equal to 1 to m xi into the weights wik, k from 1 to m. So if you write the input of 1, that is xi wi1, so it is x1 w11, then x2 w21, which is w12, then x3 w31, like that. Multi-layer feed-forward networks. This network includes at least one hidden layer in addition to the input and output layers. The hidden layer is internal to the network and does not interact with the external environment. The presence of hidden layers enables the network to model more complex relationships and perform stronger computations. This architecture is also known for its ability to handle nonlinear data. So there is input layer, x1 to xm, hidden layer y1 to n, then it is the output layer, that is 1 to r, z1 to zr. So here the input of k is summation of I equal to 1 to m xi into wik. Z input is that summation of I equal to 1 to n y output I into the weight, that is wik dash. So these are the weights here. The next, which is the third one, is that single node with its own feedback. In this type of network, the output of a single node is feedback as input to the same node or to preceding nodes. This feedback mechanism creates a loop in the network and is the foundation of the recurrent networks. The node with feedback can use its own output as a part of its next input, forming a closed loop that can lead to dynamic behavior over time. Next one, that single layer recurrent networks. A single layer recurrent network is similar to the single layer feed forward networks with the addition of feedback connections. In this case, the output of processing element can be directed back to itself or to the other processing elements, forming a loop. This feedback capability allows the network to handle sequential data and maintain memory of previous input, which is useful for tasks like time series forecasting or speech recognition. Multi-layer recurrent network. In this network, feedback connection exists not only within the same layer but also between the different layers. The output of processing element can be feedback to both preceding layer and within the same layer, forming a more complex feedback loop. These multi-layer recurrent networks are particularly suited for handling sequences of data where the network needs to remember and process information over multiple time steps, such as natural language processing or video analysis. In the context of artificial neural networks, several learning techniques are used to train and optimize the model. Here is a brief summary of the key learning techniques. First one is that supervised learning description. The model is trained on a level dataset where the correct outputs are provided. The goal is to learn a mapping from inputs to outputs, common algorithm, backpropagations using gradient descent to update weights, example image classification or regression tasks. Second one is that unsupervised learning. The model learns patterns from unlabeled data without explicit outputs. It aims to discover hidden structure in the data. Common algorithm, autoencoder, coherent self-organizing maps, that is SOM. Example, clustering data or reducing dimensionality. Next one is that reinforced learning. The model, that is agent, learns by interacting with an environment and receiving feedback, that is rewards or penalties, based on its actions. The goal is to maximize cumulative rewards over time. Common algorithm, Q learning, deep Q networks, DQN, policy gradients. Example, game playing, robotic control. Fourth one is the self-supervised learning descriptions, a form of unsupervised learning where the model generates its own label from the data. It learns useful features by solving a pretext task, example, prediction missing data. Common algorithm, contrastive learning, predictive learning, example, language model, that is GPT, BRT for text. Transfer learning, a pre-trained model is adapted to a new task with minimal additional training. Knowledge learned from a related task. Common algorithm, fine-tuning pre-trained networks like ResNet, VGG, PRT. Example, using a pre-trained model on ImageNet for new image classification tasks. Online learning, the model is updated incrementally as new data arrives, suitable for situations where data cannot be stored all at once. Common algorithm, stochastic gradient descent, SGD, real-time recommendation systems, and financial forecasting. Each of these techniques helps train and optimize ANN models for specific tasks, and the choice depends on the problem, data availability, and model objectives. Next one is activation functions. Activation functions in neural network introduce nonlinearity, allow the model to learn complex patterns and relationship in data. Without nonlinearity, the neural network would only be able to learn linear mappings regardless of the number of layers. This is where activation functions play a crucial role, enabling the network to approximate more complex functions. Here are some commonly used activation functions, each with its own characteristics and use cases. First one is the sigmoid, that is logistics. Formula sigma x equal to 1 by 1 plus e to the power minus x. Range is from 0 to 1. Characteristics smooth and differentiable. Output probabilities often used in the output layer for binary classifications. Disadvantage can cause vanishing gradients for large positive or negative inputs. Next on the hyperbolic tangent, tan hyperbolic, the formula is, you know, that e to the power x minus e to the power minus x by e to the power x plus e to the power minus x. That is 2 by 1 plus e to the power minus 2x minus 1. Range minus 1 to 1. Characteristics similar to sigmoid, but output values between minus 1 and 1 helps the centering data. Disadvantage like sigmoid, it can also suffer from vanishing gradients. Next on the rectified linear unit, ReLU. Formula for ReLU is x is that maximum of 0 and x, that is 0 to infinite range. Characteristics simple, computationally efficient, and widely used in hidden layers. Helps reduce the vanishing gradient problems. Can cause dead neurons, that is inactive neurons, for negative inputs and leading to sparse activations. Next one, that leaky ReLU. Formula for leaky ReLU x is maximum of alpha into x, and x or alpha is a small constant. Range minus infinity to plus infinity. Characteristic variant of ReLU that allows small negative values to flow when x is less than 0, which helps avoid dead neurons. Disadvantage, the choice of alpha is a hyperparameter that needs tuning. Next one, softmax. So xa is that e to the power xa by summation of j e to the power xa 0 to 1 for each output neuron with the sum of all outputs equal to 1. Characteristics converts a vector of raw scores into probabilities for multi-class classification problems. Can be computationally expensive when the number of classes is large. F Swiss, the next one is Swiss. So formula for Swiss X is X into sigma X, range minus into plus infinity. Characteristic: a smooth, non-monotonic activation function. It has shown promising result in deep networks, more completely expensive than ReLU. Next one is that exponential linear unit, that is ELU. The formula for ELU is x if x greater than 0 and alpha into e to the power x minus 1 if x less than equal to 0. Range from minus alpha to infinite. Characteristics similar to ReLU but smooths out negative values. Helps speed up learning by reducing the vanishing gradient noise. More complex than ReLU. Next one is that sigmoid scaled ReLU, that is scalable ReLU. Formula for scalable ReLU X is that maximum of 0x into sigma x. Range is 0 to 1. A combination of ReLU and sigmoid used to enhance performance and avoid dead neurons. This is computationally heavier than regular ReLU. The next one is that the back propagation algorithm. The back propagation algorithm is a supervised learning technique used for training artificial neural networks. It helps minimize the error in the network by updating the weights of the network in the direction that reduces the output error. There is a high level overview of how the back propagation algorithm works. Step 1, that is forward pass. The input layer, the algorithm takes the input data and passes it through the network. Each layer performs a set of mathematical operations such as matrix multiplications and activation functions to process the data. Hidden layers, the input data is passed through the hidden layers where each node, that neurons, performs computations based on the inputs and its weights. Output layer, the final output layer produces the network's prediction or output. During the forward pass, the network generates an output using the initial weights and biases. Step 2 is that compute the loss, that is error. After the forward pass, the algorithm computes the loss or error by comparing the network's output with the true target, that is expected output. The common loss functions include mean squared error, that is MSE, for regression problems and cross entropy loss for classification problems. Step 3 is backward pass, that is back propagations. The goal is that the goal of back propagation is to minimize the loss by adjusting the weights, that is gradient calculation. The back propagation algorithm computes the gradient of the loss function with respect to each weights in the network using the chain rule of calculus. For each neuron in the output layer, the gradient of the loss is calculated based on the difference between the predicted and actual output. Then the gradient is propagated backward through the network layer by layer. At each layer, the algorithm calculates how much each weight and bias contributed to the error, adjusting them accordingly. Step 4 is that update the weights, the gradient descent. The weights are updated in the direction opposite to the gradient to minimize the loss. This is done by using the gradient descent or its variants like stochastic gradient descent or ADM. The formula for weight update is that W equal to W minus eta, uh, that del L by del W. So it is W equal to W minus eta del L by del W, where eta is the learning rate, L and that L is the loss function and W is the weight. Then iterate the process of the forward pass error calculation, back propagations, and weight update is repeated for many iterations until the network performs convergence. That is when the loss step significantly decreases. Key concept: first one is chain rule. Back propagation uses the chain rule of calculus to propagate gradients from the output layer back to the input layer, allowing the network to update and weights appropriately. Activation functions like ReLU, sigmoid, or 10 hyperbola or introduce nonlinearity to the model, enabling the network to learn complex patterns. Learning rate. The learning rate controls how large the steps are when updating the weights. If it's too high, it can cause overshooting. If it is too low, it can lead to slow convergence. So conclusion is that in this class we have understood the basic concept of artificial neural networks. The question for today's class is that compare different learning techniques, that is supervised, unsupervised, reinforced learning, etc. So these are the references of today's class. Thank you.